Hey, folks. All right, got some more equilibrium examples for you. And again, nothing new, just two things. Net force is zero and net torque is zero. But we're just applying that in a lot of different examples here to kind of get you used to how to do that. So the next example I've got for you is a ladder. So let's say you've got yourself a ladder, see? And I'll move this up here. Okay, and let's say it's me at Christmas time and I am putting up decorations. Okay, so let's say that this is leaning up against the wall. Okay, and then it's also on the ground here. And let's say that I am 3/4 up the ladder. So I am up here. Okay. Now, here's the deal. And let's give you some statistics here. Let's say the length of the ladder is 8 feet. Okay. Let's say the mass of the ladder is 20 kilograms, and it's a light ladder, and the mass of me is 100 kilograms. Okay, now that's a little over what I actually am. Let's say I got all my Christmas gear and stuff that I'm carrying up there. So let's say it's 100 kilograms. And let's say that the distance between the base of the ladder and the wall is 3 feet. Okay. Okay. So the length of the ladder, 8 feet, is 3 feet from the base of the wall. And for this problem, here's what we're going to figure out. Assuming the wall doesn't have much friction, in other words, it's slippery, or a lot of ladders will actually have a little wheel up here, which makes friction roughly zero. So assuming that there's little to no friction between the ladder and the wall, right? What is the minimum coefficient required between the ladder and the ground so that the ladder doesn't fall and make Mr. Mashar hurt his head or anything else while he's putting up Christmas decorations? Okay, so as all the other problems have started, we're going to start with an FBD. Okay, so now if you haven't had a chance to draw this yet, you can just draw a line here. Okay, now remember, I am 3/4 the way up the ladder. Okay, so that's important to know. Okay, so I'll draw the FBD right in the picture here. Okay, well, at least you know what? I'll do a sketch in the picture, and I'll draw an FBD below and make it a little clearer. So, but what forces act on the ladder? Okay, well, you're going to have the wall pushing this way. You have the normal force of me, which will equal my weight. You're going to have the weight of the ladder. You're going to have the normal force between the ground and the ladder, and you're going to have friction keeping the ladder from actually falling. Okay, so let me draw this as an FBD over here with some of the less of the stuff to worry about. All right, so we got that. We have my weight, which will be big mg. Now, again, it's not really my weight, it's my feet pushing on the ladder, but it's going to equal my weight. We have the actual weight of the ladder itself, that's little mg. We have two normal forces, one from the wall on the ladder and one from the ground on the ladder. I'm going to call the wall one, I'm just going to call FW for wall, just to kind of keep myself straight here. The ground one I will go ahead and call F normal, and then we have friction pointing this way, which will hold the ladder in place. Okay. Okay. So now we have a couple dimensions here. So this angle right here, we'll see if we actually need it or not. But I will remind you, the length of the ladder is 8 feet. The distance from the base of the ladder to the ground or to the wall is 3 feet. If you do Pythagorean's theorem and find the height of the ladder, it's root 64 minus 9, 8 squared minus 3 squared. So it's root 55, okay? So I'll call this angle here theta, but we may not actually ever need to really calculate it if we have all three sides of that right triangle. Okay, so let's start with net force. Okay, so net force in the x direction equals 0. Okay. All right, so net force in the x direction is 0. Now, luckily, we only have two forces in the x direction, F wall and FF. So we know that the force of friction has to equal the force of the wall. And then we'll do net force in the y direction equals 0. Okay. And in the y direction, we have one upward force, that's our normal force from the ground, and we have the two weights acting down, basically, the person's weight and the ladder weight. So we've got force normal is going to be equal to big mg plus little mg. All right. So we got three unknowns, though. We don't know friction, we don't know wall, we don't know normal force. So we need a third equation to solve for these, and that's where you're going to do your net torque. Now, again, you want to look for places, convenient places to do net torque, okay? And I'm going to pick the very base of the ladder as my axis, because then I eliminate friction and normal force as unknowns, and the only unknown that'll be in that equation is the force of the wall. And I'll be able to solve for the force of the wall directly, okay? So I will use this. I will use clockwise as positive. And this is definitely one where using ratios and perpendicular lever arms just make life so much easier. All right, so for instance, let's start with the weight of the ladder. That's little mg. So if I draw a line straight down, that line of force, okay, what's the smallest distance, the perpendicular lever arm from our axis to that line of force? Well, you don't need to do a bunch of trig for this, okay? If you look over here, okay, the way the ladder's at the center of the ladder, which is going to hit the center of this 3 feet, which is 1.5 feet away. So this is 1.5 feet, okay? And then the same thing with my weight, or my normal force, which is equal to my weight, okay? I am 3/4 up the ladder, so this is going to be 3/4 of 3 feet, which will be 9/4. Okay, so those are those two perpendicular lever arms. Now, the force of the wall, it's a little tougher. So that line of force goes left and right here, horizontal. What's the shortest distance from that line of force to the base of the ladder? So this black line, the dashed line that I'm drawing, that's your perpendicular lever arm. That's the height of the wall, which we figured out was root 55. Okay, so I have that number. So the cool part is on this, I don't need the angle. I have my 3 lever arms. It's 1.5 feet, it's 9/4 feet, and it's root 55 feet. Okay, now all I got to do is figure out clockwise and counterclockwise. So I'll do net torque about that base, or about that axis, equals 0. So we start with the weight of the ladder, so that's little mg times its lever arm, which is 1.5, okay, plus my weight is also trying to rotate the ladder clockwise, so that's big mg times 9/4 of a foot, all right, and then the wall is trying to make the ladder go counterclockwise, so that's a minus force of the wall times root 55, and that all has to equal 0, okay? Now, remembering that little m is 20 and big M is 100 and g is 9.8, you got everything here except for force wall. And if you plug the numbers in your calculator, you should get the force of the wall is 337 newtons, okay? So double check me and make sure you guys get that. All right, now the cool part is that equals the force of friction. All right, so the force of friction is 337 newtons. And then the force normal, well, I know that. That's just equal to the two weights added together, which is 20 times 9.8 plus 100 times 9.8. Okay, so that would be 980 plus 196. Okay, which would be whatever that is, 980 plus 196, I get 1770 or 1176, sorry. So that's the weight of the two things combined, which is going to be your normal force. And then our minimum coefficient of friction, this would be static friction. You're hopefully not sliding, it's not kinetic, would equal force of friction over force normal, which would be 337 over 1176, which I get about 0.29. Okay, so my coefficient of friction between the floor or the ground and the ladder better be at least that. Otherwise, it's going to slip out from underneath me and I'm going to be in trouble.